Hey guys, Eric Magnuson here. I'm here to present my EE452 Embedded Systems project. For my project, I did a PLC installation on a Babcock dryer. The control system we're talking about today is a veneer dryer, and you can see the picture on the left. This is a very large system. The picture in the center, that's actually inside the dryer. You can kind of see the rollers and the ductwork that provide the drying to the veneer. And on the right, you can see our finished product, the actual veneer we produce here. Now in embedded systems, we kind of talk about peripherals a lot. We're talking about the inputs and the outputs from the system that come back into the embedded system. The things that allow the embedded system to make the decisions in the process. And you can see this is the feedback we're getting from this system. On the top left, you can see temperature control. You can see dampers that are automatically controlled to exhaust the system. And they also provide feedback. On the bottom left, you can see humidity controllers. And on the right hand side, you can see different steam devices. This is proportional valves that are allowing steam into the dryer to heat the process and also measure the steam entering so we know what temperature is entering. The principles of the veneer dryer are we bring in cold air from outside and we bring it into the dryer and we heat it up to about 300 degrees Fahrenheit. We circulate that heated air over the veneer, and that heated air absorbs the moisture out of the veneer, drying the veneer. The dryer maintains humidity and temperature inside of the dryer through proportional control in both an exhaust damper and proportional control coming into the heat exchanger. Them are the only two automatic controls of the dryer. So when we're talking about programmable logic controllers, or PLCs, we're talking about a modular system. Typically the processor is a standalone unit that mounts into a rack, and that rack connects to a lot of different peripherals that processor can use to communicate or control the outside world. So when I'm talking about the different peripherals, I'm talking about digital I/O, I'm talking about analog signals coming in or out, so digital to analog conversion or analog to digital conversion. I'm talking about different communications topologies, either network based, it could be a serial, it could be servo control, but basically everything for the processor to communicate to the outside world and control that world. And something to remember with mechanical systems, especially in manufacturing facilities, there's often a safety system that is over top of the PLC that overrides any output from the PLC. So these are electrical mechanical backup and safety systems. Sometimes they can just delay or disable the output, or they can physically block it with a barrier. But it's something to remember, just because the PLC tells the system to do it doesn't mean it actually happened. So because of that, we need external environmental feedback. We need to know when we send a command out, did that actuator actually go out, or did that motor actually turn? And that's feedback that comes back into the input peripherals and is converted back from analog to digital, and that's the feedback loop that happens in a control system. And specifically in this dryer that we're going to be talking about, there's a lot of these feedback loops that the dryer uses to control the process. For this installation, what we did is we replaced the existing PLC. It was a German-based PLC that had become obsolete. The company no longer produces it, and they don't no longer support it. If you go into manufacturing engineering, you're going to work with a lot of this, replacing obsolete equipment with the latest and greatest. I mean, just like technology, like your home computer, every 5 to 10 years things are obsolete. They don't exist anymore. They're hard to maintain. The software is too old. It doesn't work with the new systems. So as part of stability and reliability in a plant, you have to constantly be maintaining and upgrading this equipment. And the new equipment often offers different advantages, whether it's better system stability, better longevity for the system, easier access, easier controls. You know, there's a lot of reasons to do it. For this system, one of the big advantages was we were able to introduce new HMI controls that allowed the users to have a lot more flexibility in their different entering parameters, or they're viewing the system, whether it be outputs going out into the field or inputs coming back, different variables. On this screen you can see the variables that the users have control over. They can control temperature, they can control humidity, they can control the transport speed. And what happens in the background is the embedded system takes in that information from the user and it uses it to perform all of its calculations that it uses then to run the system. A big part of this project was data recording. We wanted to be able to monitor how the dryer ran over time. so that we could increase the stability of the system. You can see in this we have an unstable system. That black line's moving up and down over and over and over, and the valve it controls is moving up and down over and over and over. So in able to monitor that system, we needed some type of control where we could record it and monitor it and then adjust it. Another important aspect of this project was alarms. We wanted the system to be able to communicate to the operator or the user when it had problems. We wanted to record what the problem was, when it happened, so that when the user came and cleared that fault or error and restarted, we could go back and look at the history. How many times did this happen? When was the last occurrence? And with that, we can direct maintenance activities around that. But we need that feedback from the system. On this slide, we can see an instability in the system that we identified through that data collection. We found that damper 1 was operating very erratically throughout the entire run, and this was allowing a lot of the heated air to exhaust up and through the stack. And what this does is it causes the dryer to use a lot more energy than it needs to, and it also reduces the amount of airflow onto the veneer, so it reduces drying. So when this is operating erratically like this, we get erratic output out of the dryer. You can see here the before and the after. So the before is before we made these changes and we were just monitoring the system to see how it operated. After, you can see we have much more stability. The damper is now under control, and it also related to the output of the dryer, which is the moisture in the veneer. The moisture in the veneer is now also much more stable. So the results of this system change: more connectivity, better system stability, adaptability, and standardized recipes. This equated to energy savings of about $32,000 annually. We measured the airflow leaving the dryer, and we were able to capture the amount of heat we were exhausting to atmosphere, and we can correlate that back to natural gas usage. We were also able to reduce the amount of fans we needed to run to dry the same amount of veneer, which saved us significant amounts of money in electricity. Thanks guys, that's my project. Have a good one.